Ever feel it? The more you learn about something really complex, the more confusing it actually gets.
Oh, definitely.
Yeah.
Especially with conflicting sources.
Right. And what if the very way we measure something as basic as energy, wasn't quite consistent? Like having, I don't know, different sized inches on different rulers.
That's a great analogy.
Well, that's kind of the shocking idea behind a groundbreaking study we're looking at today. It suggests this inconsistency could be messing with our whole energy transition.
It's a really significant claim.
So today we're doing a deep dive into this crucial piece of research, the necessity to standardize primary energy quality in achieving a meaningful quantification of related indicators. Quite a title.
Yes, it's specific, but the implications are huge.
Our mission here is basically to change how you look at energy data.
Right.
We want to unpack why comparing, say, solar power to natural gas isn't just about the final numbers, it's way tricky.
Much trickier.
And we'll look at what this study suggests as a fix for, well, a really fundamental scientific problem. Think of this as your shortcut to getting informed on something vital for our energy future.
It's certainly timely. I mean, humanity's right in the thick of this massive energy transition.
Absolutely. Moving away from fossil fuels towards renewables.
Exactly, which is vital, obviously. But these newer technologies, they have their own challenges. Things like managing intermittency, needing different materials. And sometimes the energy itself might be of a different quality, even if the quantity seems okay. So comparing them accurately is, well, it's essential if we want to make smart choices.
And we rely on certain tools, certain metrics to make those choices, right? Things like EROI, energy return on investment.
Yep, EROI, and also CED, cumulative energy demand. These are supposed to give us the real picture of energy costs and benefits.
But what if those tools themselves are shaky, based on flawed calculations?
That's exactly what this study argues.
Mm.
It points to a fundamental gap in how we quantify what's called primary energy.
Okay, primary energy. Remind us what that is again.
Sure. It's basically energy as it exists in nature. So think raw crude oil, sunlight hitting the earth, the energy in wind or a waterfall. It's the raw stuff we then convert into useful energy carriers, like electricity or petrol.
Got it. Raw ingredients.
Right. And the study's big claim, which is pretty startling, is that our current way of estimating this primary energy lacks, and I'm quoting here, scientifically justifiable grounds to compare any parameters that depend on it.
Wow. Okay, so not just a minor issue. It's saying the very basis for comparison is scientifically questionable.
That's the assertion. It's not just fiddling with numbers. It's a core problem.
It really is like that apples and oranges thing, isn't it? But maybe worse, like the definition of fruit changes depending on which aisle you're in.
That's a good way to put it. The study actually quotes Cranan et al., asking this very pointed question. How do you account for the joules contained in a barrel of crude oil and the kilowatt of electricity from a solar panel in a single metric?
You can't easily, right, if the underlying measurement isn't consistent.
Exactly. And this study argues that's why current methods make EROI, which should be a straightforward ratio, unsuitable for really comparing one technology directly against another, or one whole energy system against another.
So if we look back, how did we even get here? What were the past approaches?
Well, researchers like Cran et al., whom the study references, identified different ways people have tried to quantify this.
Yeah.
Primary energy quality, or PQ. There are various methods. Partial substitution, direct equivalent.
Different ways to convert the raw energy into a comparable number.
Sort of, yes. But the problem is they give wildly different results.
Like the wind power example you mentioned earlier. That sounds pretty stark.
It really is. The study points to data, like in their Table 1, showing that for wind power, depending on who's calculating and which method they use, say BP versus the IEA, the conversion factor to primary energy could be anywhere from 26%.
Only 26%.
All the way up to 100%. A huge range for the exact same physical process of wind generating electricity.
That just screams arbitrary, doesn't it? How can it be both?
It highlights the, let's say, the lack of standardization. And the potential for bias, intentional or not, is obviously there.
Okay, so simple methods are inconsistent. What about more complex ones? I've heard of exergy. Does that help?
People have tried using exergy, which is basically the maximum useful work you could get from an energy source. It's more sophisticated thinking about energy quality.
Right.
But even that falls short, according to this study, because most energy statistics, the things we use for ERI and CED, they're based on the final energy we actually use, like the kilowatt hour of electricity coming out of the wall, not the theoretical maximum potential of the original source.
So we're still measuring at different points, in effect.
Pretty much. A joule of high-quality electricity can do much more work than a joule of low-grade heat. But current primary energy accounting often doesn't capture that quality difference properly when tracing it back.
So, boiling it down, the study, citing Lightfoot, suggests the joules we talk about aren't really the consistent joule from physics class, that they're kind of arbitrary units.
That's the core and very provocative claim, that these energy joules used in statistics cannot be matched to the joule defined in physics and chemistry, which implies a potential violation of key scientific principles.
Okay, that's a big statement. What are these scientific principles they say are being violated? This sounds fundamental.
It really is. The study argues there are three main violations happening. First, a lack of what they call measurement consistency.
Mean.
Meaning, like your ruler example, a physical thing should be measurable the same way, with the same accuracy, no matter who measures it or what form it's in. Think of a kilogram. It's a kilogram, period.
Right, standard.
But for energy, particularly primary energy, this study says that consistency just isn't there across different sources and different organizations.
So, principle one is consistency. What's the second?
The second is the neglect of energy quality. This is crucial. When deciding where in the process to measure the primary energy for, say, coal versus solar versus hydro, the inherent difference in the quality of that energy at the source was often ignored.
So, we might measure the heat energy in coal before burning, but the electrical energy from hydro after conversion, and treat them as somehow equivalent primary inputs.
That's the kind of inconsistency it leads to. The result is that the same amount of final electrical energy can end up being assigned wildly different primary energy values depending on where it came from, because the quality wasn't factored in properly at the start.
Okay, consistency, quality, and the third violation. This goes back to the joule itself.
Exactly. The third is about the arbitrary joule. We think of a joule as fixed, right? But the study points out it's a derived unit, not fundamental like the kilogram.
Derived meaning it's based on other units, like force and distance.
Correct. And how you measure that joule is very different depending on what you're measuring. The joule representing the chemical heat in fuel is measured differently from the joule of kinetic energy in moving water, or the joule of radiation hitting a solar panel.
Ah, so the measurement method itself introduces variability.
It introduces variability in the meaning and quality associated with that joule. It's not like weighing things on a standard scale. The study argues this makes comparing joules across different forms without careful quality consideration scientifically problematic.
Wow. Okay, so the study lays out these fundamental issues. How did they go about actually testing this? What was their method?
They took a really systematic approach. They used life cycle assessment, LCA databases, specifically EcoInvent data, which is quite detailed.
LCI tracks everything, right? From cradle to grave.
Exactly. All the energy, materials, everything that goes into making something or providing a service. It's perfect for seeing how these different energy inputs are actually tallied up in practice. They use this data to test two key hypotheses.
Okay, hypothesis number one.
Hypothesis one was about cumulative energy demand, CED. Remember, that's the total primary energy used to make a product.
Right, the whole life cycle energy costs.
So they set up this clever scenario. Imagine making the exact same product, same factory process, everything identical, except for the electricity source. They modeled it in two hypothetical countries. One used mostly fossil fuels for its electricity. The other used mostly renewables, hydro, wind, solar.
And the product itself used the same amount of electricity in both cases.
Precisely the same amount of electricity consumed by the process. But here's the kicker. What they found in their table 4, the calculated CED for that product changed dramatically.
Just by changing the electricity source, even though the electricity used was the same, how much did it change?
Significantly. When they replaced just 50% of the fossil fuel electricity with hydropower, the CED dropped to 78% of the original value.
Wow.
And when they replaced all the fossil and nuclear power with a mix of renewables, hydro, wind, solar, and taxity, the CED plummeted to just 50% of the baseline value.
Half. For the same product using the same amount of electricity? That's staggering.
It really is. And it's powerful evidence for their claim. It shows that just adding up primary energy megajoules from different sources, like we do for CED or total primary energy, TPE, well, it lacks consistent, scientifically justifiable meaning.
Because those megajoules aren't truly equivalent. They represent different qualities.
Exactly. You're adding up these arbitrary MJ units, as the study puts it, without a proper basis for comparing their actual energetic value or quality. The units look the same on paper, but they hide vastly different realities.
That's a huge takeaway for anyone using CED figures. Okay, what about the second hypothesis? That was about EROI.
Yes, hypothesis 2 tackled the EROI comparability problem. EROI, again, is energy out divided by energy in. It should be a simple, dimensionless ratio you can use to compare
It
technologies.
should be.
Right. So the study calculated EROI in three different ways. One used the traditional primary energy approach, EROI PRTR. Another was based purely on the electricity output and input, EROIL. And a third used a primary energy equivalent method, EROI PEQ.
Okay, three different EROI calculations. Did they give the same answer?
Well, for fossil fuel power plants like gas turbines or coal plants, the results from the different methods were pretty close. Comparatively equivalent, as the study says, which is good. That suggests consistency for those.
But I sense a but coming.
You sense, right. But for the renewable energy technologies, solar PV, wind, hydropower equipment, the EROI values were significantly different depending on which calculation method they used. Massively different.
How different are we talking?
The study found the relative difference between the electricity-based EROI, and the traditional primary energy EROI PRTR for renewables was often over 100%, sometimes up to 133% or even more for the equivalent method.
Over 100% difference. So the EROI number could literally double or more just based on which accounting method you pick.
Precisely, which leads to their crucial finding.
Let me guess. This introduces a bias.
Bingo. It means current EROI methods, particularly the traditional ones, introduce a significant bias against all renewable technologies when you try to compare them to fossil fuel generators.
That's incredibly important. That could skew policy, investment, everything. Why does this happen? Why the huge difference specifically for renewables?
The study uses its figure 2 to illustrate this. It essentially shows that the way primary energy is currently counted, you need vastly different amounts of primary energy to get the same unit of electricity, depending on the source.
Give me an example.
Okay, according to current estimates they analyzed, to generate 1 unit of electricity, you supposedly need about 10 primary energy units of geothermal heat, or maybe 3.3 units from biomass, but only about 1 unit from hydropower.
So hydro looks incredibly efficient in primary energy terms, while geothermal looks much less so, even if they produce the same electricity.
Exactly. And the study argues this happens because the reference point for measuring that initial primary energy was set differently for different resources, without really paying attention to the quality of that energy at the source.
So we're back to that core issue of neglecting energy quality right at the start of the calculation.
Yes, it bakes the inconsistency in from the beginning, leading to these biased EROI figures for renewables.
Okay, this is a deep problem. We've got inconsistent measurements, neglected energy quality, arbitrary joules, biased metrics. It sounds a bit of a mess.
It highlights a significant challenge, certainly.
So what's the way out? Does the study offer solutions? How do we fix something this fundamental?
Thankfully, yes, it does propose solutions. It argues fixing this is crucial for, sensible energy planning. They suggest both a short-term practical fix and a more fundamental long-term goal.
Okay, what's the short-term fix? Something we can do now.
The easiest way forward immediately, they suggest, is to pick a common output with a consistent energy quality as the reference point for comparison. And the most logical choice for that is electricity.
So instead of trying to equate the different inputs, primary energy, focus on the common output, electricity.
Exactly. Since so many systems generate electricity, you can use that as your standard benchmark. Standardize the joule at the quality level of electrical energy.
How would that work in practice?
Well, you'd then need scientifically sound conversion factors to translate the primary energy inputs of different sources, like heat, wind, kinetic energy, solar radiation, into this standard electricity equivalent unit. Table 5 in the study gives an idea of how this might look.
So you'd adjust the primary energy values to reflect their quality relative to electricity.
Precisely. This would allow for a much fairer comparison, and it reinforces their finding that the EROI calculated purely at the electricity level, EROIL, is really the only truly comparable EROI because it's based on a consistent quality level and is genuinely dimensionless.
That makes sense. A pragmatic approach using electricity as the common denominator. What about the long-term vision?
The ultimate goal, the truly fundamental fix, according to the study, is to actually standardize the unit joule itself.
Standardize the joule, like we have a standard kilogram in Paris.
Exactly like that. To give the joule a single definite value, similar to kilogram, that applies consistently across all forms of energy and all areas of science and statistics that use it.
That sounds ambitious. It would mean rewriting some fundamental definition.
It would be a major scientific undertaking, yes. updating definitions, ensuring measurement protocols are consistent everywhere, regardless of the energy form. But the payoff would be enormous
How so? Why does this matter so much to, us, the listeners, and our energy future?
because, as we've discussed, the current inconsistencies actively introduce a significant bias against all renewable technologies. This isn't just numbers on a page. It shapes reality.
It affects which technologies get funded, which policies get enacted.
Absolutely. It influences multi-billion-dollar investment decisions, government incentives, research priorities, our whole perception of which path is best for the energy transition. If the measuring stick is skewed, the choices we make based on it will be skewed too.
So standardizing, whether via the electricity reference or ultimately the joule itself, would finally allow for real, meaningful comparisons.
Yes. Truly meaningful technology to technology, technology to system, and system to system comparisons using metrics like eROI. It would remove the current bias and resolve the problems we see with CED and other energy stats.
It's really about ensuring our scientific tools are actually fit for purpose, accurately reflecting physical reality so we can navigate towards a genuinely sustainable future.
Exactly. Building that future on solid, comparable data, not on units that shift their meaning, depending on the context.
Okay, we have just taken a deep dive into the necessity to standardize primary energy quality and achieving a meaningful quantification of related indicators.
A crucial topic.
And the really surprising takeaway, I think, is that the very joule of energy we rely on can represent different qualities, leading to these deep inconsistencies, biasing our view against renewables, and, well, potentially hindering our path forward. So the question for you listening is, what stands out to you about how we measure energy, and how might fixing this fundamental scientific challenge actually reshape our energy decisions in the coming years?